Okay, are there any questions over any of the homework problems or anything you want to discuss? They took a lot of time. Sorry?
Did we have to do up to 32 or 32?
I don't remember. 30, 30, that's fine. If you looked at those reduction formula problems, I mean, that would appear on the test as a bonus. So, the reduction formula ones? Who has the book? I don't carry it around because it's too much to lug around. I'm going to pass around your quizzes. Is that all right? Anybody have any objections to me passing around the quizzes, or do you want to come up and grab them so that no one sees your score? Pardon? I will be in my office, yes. Any objections? Can just pass these around? Is that an objection? It's all right. Alexis messed it up. Okay, so I'm going to pass these around.
Thank you, sir.
That's from last time. All right, so I'm going to just look at the. I'm referring to the reduction formula problems out of 6-1. I said bonus on this test. 35 through 38. Yeah. 35 through 38, and actually 31 through 38, because I think 31 is where it starts talking about reduction formulas. Okay, so no?
Yeah, I have a question.
Okay.
Number
15?
Oh, yeah, man.
Yeah, that was the ugly one. I'm silencing my phone. Was it the one we were just talking about, the x, e to the 2x over 1 plus 2x dx? This is number 15. Oh, this thing is squared down here? It's probably the hardest problem, I think, in the entire homework assignment, maybe. It's not necessarily the longest, but it's the hardest to see what u and dv are going to be. So, I don't know. It's hard to even see this as integration by parts because you're trying to, pick something for u that when you take its derivative, it's going to get nicer. And then when you pick something for dv that when you integrate it, it's going to be something nicer. Or that when you put them together, right, the voodoo in the new integral is going to be something you can handle. So do you just want to see how to do it, or do you want me to talk through more like how, like, we're coming up with that? What do you want, Nolan? Did you ask about it?
Oh, that was the one I had to ask about, yeah.
Yeah.
So I watched the video and I don't know. It's kind of just like, oh, what?
Yeah. Yeah, okay. Yeah, and that's the thing. This substitution is not what you necessarily would see right away. I don't know. I don't see the value in a problem like this because you could get hung up for a while on this. And that's not the intention of the test, is try and give you an integral that's going to hang you up. The things I would expect are things that I think would be obvious, which would be a problem like take the whole bottom out of this. And then that right there should be much more in line. You know what I'm saying? That would be, just let that be u and that be dv, and then you're off to the races. So, so the substitution you make for u here, I believe, is this. And then dv is everything here on the bottom, right? But it's 1 over that, right? Because it's on the bottom. So it's 1 divided by this. So this is 1 over 1 plus 2x squared dx. That's how you would first write the problem out. And then from there you go through and take the derivative of this. But that's a product, so you're going to get a product rule there. And so you get e to the 2x plus the derivative of e to the 2x, which is 2 e to the 2x but then times x, finishing off product rule, all of that times dx. Since there are two terms, I'm going to put it in parentheses. And so even right here, you're like, whoa, you know, like this does not look good. But then you have to integrate this up, which might be some work that you have to do on the side to like figure out what that is. I won't go through it. Just going negative 1/2. You could do from here to here by basically doing this problem right here. 1 over 1 plus 2x squared dx. Do that problem on your own. Make a basic u substitution of a 1 plus 2x for your u. Work through this. Get an antiderivative. When you do that, you should get this. And then you look at this, you're like, holy man, this looks terrible. But then you put it all together, you do your ultraviolet, so this times this, minus the integral voodoo. And I think I'll just write the voodoo down, because this is all on a homework video that I've done already. The voodoo part is the integral this times this. I'll pull the negative 1/2 out. And then this right here times this. What can you factor out of this? That's the key to the whole problem. You can factor out an e to the 2x. And when you do that, you have e to the 2x factored out. You have 1 plus 2x on top dx. That's this, right? But then times this, so this is on bottom, 1 plus 2x, and then they cancel completely, which saves the day. So, yeah.
When you multiply an x, when you factor out the e to the 2x, what happens to that x? That one.
The 2x?
Oh, okay. So
Yeah, this 2x is right here. Yeah. So yeah, I definitely don't see myself trying to give you something like that. To me, that's like the evil math professor who's like, you know. I'm going to create this integral that's going to take 30 minutes just to figure out maybe what's going to happen with it, okay? Hey, I'm on video recording right now. This is a good microphone.
No, it really is.
Okay, so anything else? Do y'all feel like you're ready? Do you feel like you're ready for this test? I thought of doing a homework check today. Coming by and just saying, let me see your homework. I just want to see where you are. But then I thought, you know what? This is not grade school. This is not high school. This is college, and I shouldn't have to lead you by the hand, right? So hopefully you've done all your homework. I've offered you opportunities to ask questions. The test is on Thursday. We ran through last semester's exam last time. I'll just breeze through it again. This is just so you don't lose sight of the fact that this exam is going to go back and cover stuff from the very beginning, which was not integration. So there's some inverse trig stuff that you're going to need to know. I mean, and again, this is not the copy of your test. I'm not going to just go in there and change this 7 pi over 6 to pi over 3 and just rewrite the whole test. You may see something completely different, but just gives you some idea. Finding derivatives of inverse trig functions using chain rule. Let's see here. Proving an identity. Do you think you could prove an identity?
Yeah.
Do y'all like those problems?
No.
You don't like those problems. I'll make sure I put a few on there. You'll definitely see something like this, where you have to go back, you start with the second derivative and go back and recover the original function. The big question is whether or not I'm going to give you these conditions, or whether or not I'm going to give you information about the derivative and the original function, or just the original function. That's really the question. Yes?
On that, like, because in the homework, they like plug both of them in at the same time, so to speak. And in the last function, I didn't understand that.
Because there were two unknown.
Yeah, but don't you have to find like the first derivative and go find the regular problem, the original problem, and plug them in?
I'm not quite sure what you're referring to.
I'll ask you later.
Yeah, ask me later, because I don't want to talk about it if I'm not clear on what it is you're referring to. And this is where the integration began at this point. So that's just, you know, I think I showed you when we first were doing power rule, we started out with very basic stuff, and then I said, hey, this is a problem I like to give on tests because it requires students to split it up. Like this one, you have to split this apart and just use power rule. I mean, just imagine someone taking that and trying to do like integration by parts on that. Or, you know what I'm saying? You could make that really bad. But that should be something you just look at it and recognize it right away. I'm going to split that up, use power rule, be done. That's more like integration. Basic U substitution. Another basic U. Didn't we do that one in class last time? We did that one in class last time. That one we didn't, but we've seen that so many times, right? What's going to happen with that one when you do that one?
You end up getting it again?
It's going to wind up appearing on the other side again, right? And then you're going to bring it back over. Okay. This one we did in class last time. I like that problem. I really like that problem.
That's the one you have to do like multiple times, right?
That's the one where you have to peel that x cubed apart in the front
Oh, yeah.
and make the x cubed an x times x squared. I did it in last class. At the very end, I showed y'all how to do it. Yeah, do a U sub, and then it turns into an integration by parts. Okay, we haven't talked about that yet. Or that. And then see, look, I gave him that proof reduction formula. So this exam that we're taking is 15% of your overall grade. The next 3 exams after that are 25%. So this exam, although it's an important exam, if you don't do well, it's not the end of the world. If you do well, it's not smooth sailing from here. You know, like you want to get a good grade, but because the material here is very limited in scope still, the weight of the exam is not a lot. I mean, you know when the integration comes that there's really only 3 things it could be: power rule, basic substitution, or integration by parts. That's all you have, right? So, yeah. So nothing else? I'm happy to do any, problems you want to go over, anything you want to look at.
Can you do a problem like the, when you brought up the question about,
Oh, yeah,
Second
condition.
where
Yeah,
they give you
This?
like this one.
Well, why don't we just do that
They
one?
give you 2 conditions,
Yeah.
but they're both for the
Original?
function.
Like that one?
Yeah.
Let's just do that. Okay. So you're given the second derivative is 80x cubed, or sorry, yeah, 80x cubed minus 36x squared plus 6x plus 14. You're given that f of 0 is 3 and f of 1 is 8. And you're asked to find f of x. So what we do is we need to go backwards twice, right? 2 antiderivatives. So the first time we go to get back to the first derivative, we integrate these term by term. So the antiderivative of 80x to the 4th, 80x cubed, cover up the 80, antiderivative of x cubed is 1/4 x to the 4th. But when I hit 1/4, or 80 times 1/4, I get what? 20? So I'm going to have 20x to the 4th. Cover up the negative 36. Antiderivative of x squared is 1/3 x cubed. When I hit negative 36 times 1/3, negative 12. X cubed, you okay with that? And then the antiderivative of this is going to be plus 3x squared, and then plus 14x, and then plus c. All right, so had they given us information about the first derivative, right? Like let's say this had said, f prime of 0 is 3, then what I could do is I could replace all the x's with 0 and set that equation equal to 3 and solve for c. But that's not the information I'm given. I'm given information about the original function. So I cannot find c at this point. Right? Everyone agree? Cannot find it. So now I need to just integrate again. So I'm going to integrate. And I'm waving my hands. I do not know what c is. So when I take the antiderivative here, right here, so 1/5 x to the 5th, and then times 20, so what, 4 x to the 5th. Keep going. Minus 3x to the 4th plus x cubed plus 7x squared plus the antiderivative of c, which is cx, good.
Plus D.
And then plus some other constant of integration, which I don't know. I'm not going to call it c, I'm going to call it d. There we go. Yes? Yeah, thank you. This is f, not f double prime. I don't know why I put that. F. Okay.
Plug them both in at different times?
So what we're going to do first, we're going to use this information. When I plug in 0, right, for x, this thing should spit out a 3. So using the fact that f of 0 equals 3, I can say that this equation would be, we'll just replace all these with zeros, right? So all you're left with is what? D is equal to, what does it have to be equal to? 3. Well, that was easy. D is 3.
Then from there you can find C.
Yeah, well, I can use this information to find C. You know what? Man, that's almost too easy. No, I mean, just because on the test, you're not assured that on the test that that's going to come out to just wipe everything out and just have D. So can we just change the problem a little bit to make this a little more realistic?
Yeah.
All right, let's do it this way. Let's change this 0 to -1. All right, and let's go back through this right here. Do you see how by using 0, it just kills everything off and it makes it pretty simple? Yeah. Okay, let's try and plug -1 in now. What's -1 to the 5th power? -1 times 4. So we have -4. What's -1 to the 4th power? 1 times -3. Plus -1 cubed. Minus 1. -1 squared. 1 times 7, so plus 7. C times -1. Negative C. Plus D. Must be 3. Right? See, now your C didn't go away. Let's get all these numbers together. What is this number over here?
-8. Oh,
-1? Move it to the other side. So this is -1, right? So add 1 to both sides. So this becomes -C plus D is 4. Agreed? That's our first equation. We're going to save that and come back to it. Go with me? Now I'm going to use the second piece of information that f of 1 is 8. So I'll do that up here. Using the fact that f of 1 is 8, I go back into the f function, I replace all the x's with 1s. This is going to be easier to do because I don't have to worry about the signs, right? This is just going to be 4 minus 3 plus 1 plus 7 plus c plus d, right? So this means that 4 minus 3 plus 1 plus 7 plus c plus d must equal 8. Any questions on that? All right, what's the number on the left-hand side here? Should be 9, right? No? This is 1 plus 1, 9. That's 9. So go ahead and subtract 9 on both sides. Negative 1. So you get from this that C plus D is negative 1. Are we all good on this? So we have two equations, two unknowns. Right? So now we set up the system of equations, and we'll be able to figure out what C and D are. So I'll write it like we did back in the day. We use a brace. Doesn't matter which one you put on top. So C plus D is equal to 4. The other one's C, negative C plus D is 4. And then C plus D is negative 1. I was trying to avoid fractions, but... Okay, now how you do this is really up to you. You can do substitution or you can do elimination. Elimination will work right now, won't it? So just add straight down. The C's are going to cancel. You'll get 2D is what? Is 3, right? So add down, and that means that D is 3 halves. D is 3 halves. Now to go get C, you just use any equation, this one or this one, and you can just solve for C. So I'm going to use this one right here. C plus D, but D is 3 halves, must be equal to negative 1. And then subtract 3 halves from both sides. C is equal to, what happens when you take negative 1 and subtract 3 halves? Negative 5 halves? So C is negative 5 halves. And now what you do is you rewrite the whole function again. F of x equals blah, 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 blah. I'm not going to rewrite it, but, and now that C that we had, you put negative 5 halves, x, and then the constant at the very end would be plus 3 halves. Is that clear? Okay. Anything else that you want to see? Okay. I will be in my office on Thursday. Usually there a little before 9, and I'll be there till our class starts. I don't mind answering questions, helping you out. But I'll say what I said to my Cal 3 class yesterday. They have 8 take-home exams, and they get about 2 weeks for each exam. And so on the first day of class, I handed them their first take-home exam. It was due yesterday. And nobody came to my office. No one contacted me. And then it was due yesterday, which was Monday. So Super Bowl Sunday, right around 10 o'clock in the morning, my phone started exploding with text messages. People had been taking pictures of their work and sending them to me. I had like 40 or 50 text messages from students that were trying to figure out how to do these problems. 5 take-home problems. And I got to the point where it was about like 5 minutes to kick off that I responded back like to everyone. It's just like, okay, sorry, time's up. Like, you shouldn't have waited till Sunday before it's due to turn it in. So I had 14 people fail the test. I had 10 people with high A's. So I had like the people who took care of it, got it done. I had the 14 people who were texting me on Sunday. So the reason I'm telling you this is I don't mind helping you. Those of you who've come in for help know I will help you. But if you show up on Thursday morning at 9 o'clock, frantically wanting to have the answers to all your problems, it's not going to happen. I'm willing to help you. I'll push you, nudge you in the right direction, but we're not going to solve 2 weeks, 3 weeks worth of information in one sit-down session for, half an hour before. So if I see 8 people in there, that's fine, but just be aware that, the help you're going to get that day is different than the help that you would get if you came in regularly. So, am I making my point? Yeah. Not trying to scare you away, because I know that some of you just have one little thing you're just unclear on. But if you come in on Thursday and are like, I just really don't understand the whole idea of like substitution. Like when I pick something and trying to see its derivative, it's too late at that point. Okay? All right. So we're going to move on. Everybody got their Alexis? Antonio? Carmelo? He's out. Okay. I'll pass around the sign-in sheet. There's a big vertical purple highlighter. Don't sign in there. Sign on today's date, which is the 9th. Mm-hmm. And then I have a handout for you. You are allowed to bring this to your next exam. You don't need it for Thursday's exam, but the next one. And you can have it on every exam from here on out. The stuff we covered today, why don't we cover it, and then we'll talk about whether or not you want to have it. I think last semester we covered it, and they may have decided, yeah, you know what, put one of those on it or something. Maybe as a bonus. If anything, it would be a bonus. Like if I'm going to cover it, I may as well put it on the test as a bonus, right? Everybody loves bonuses. Thank you. There's what? What?
So bad at proofs.
What do you like to do on your free time? What do you like to do?
The homework now?
Weren't y'all talking about working out just a second ago? What do you like to do?
What do you mean?
Like what kind of working out?
Everything? Except
Okay,
chest,
like what do you like? What do you really like?
back.
Back. Okay. So like first time you ever did it, you are obviously not where you are now. Yes.
Yeah.
Same thing with proofs. That's what all mathematics is like. I mean, it's not some big hidden secret on how to get good at math. I mean, it's like anything else. You have to practice. It's like, does everyone know how to run a marathon? It's 26. Yeah, it's 26 miles, right, or something like that. 20. We all know what a marathon is. Could you go run a marathon right now? Like, let's go. Let's go. You know? You have to train for that. And it's the same thing with math. You have to train for it. You can watch someone do a marathon that doesn't make you able to do a marathon. You go, yeah, I see that. It's one leg followed by the other, and they're breathing. You know, that's me up here doing the math. You know, you're watching me run a marathon. That's not going to help you run a marathon necessarily. So hopefully you have put in the time and trained your brain for the test. I'm just saying a comment on proofs. You may not be good at proofs right now, but mentally you have to believe that you can get good at it if you just keep going, practicing. So, all right, we ready? Talk about today's material. Where'd it go? There it is. So this section, entitled Trigonometric Integrals and Substitutions, is actually two different topics. All right, this section, 6.2, two different topics. And we're going to try and talk about the first one. They are connected together in the sense that you can't do the second part of this section unless you've kind of mastered the first part. And on your formula sheet that I handed out, you'll notice that it says here trig integrals. Do you see that, trig integrals? And there's like these little paragraphs. You see that? And then below that, do you see where it says trig substitutions? That's where it's separated. So everything that's written like paragraphs, what I'm going to talk about today, and then the trig substitutions will come back, and that's where we'll pick up. All right? So what we're going to do with this whole trig integrals is we're trying to look at integrals that involve trig functions. We already know some of them. So do these look familiar to you? The antiderivative of sine is negative cosine. Antiderivative of cosine is sine. If we put a little scalar in front, remember that? Like a little number in front? We always have to scale by it. Okay, so we've got that. But now what we need is some sort of strategy when we have sine or cosine. We're going to start with just sine or cosine, so sine and cosine. If we ever see those together in an integral, how will we attack it? If we just see sine and cosine, and they are raised to different powers. And there's a set of steps. It's all written down here, and that's what I have in your formula sheet. And it's hard to read that, so it's better to just do an example, I think, and then we'll refer back to the formula sheet, and you'll see how I'm going to use it. But there's some important stuff that we need to remember before we can do any of this. One is the Pythagorean identity from pre-cal. We said it was an important identity. Remember that that identity can be rewritten several ways. You can solve it for sine squared, and it turns into this, right? You can solve it for cosine squared, and it turns into this. So this is just 3 different versions of that formula, right? We need to remember that. And then the other important formula for this section is what's called the half angle identity, also known as the power reducing formula, which is written right there. It's that if you ever have sine squared x, it can be written as 1/2 times 1 minus cosine 2x. And if you have cosine squared x, it can be rewritten as 1/2 times 1 plus cosine 2x. So these are things we should know coming in here today. I mean, it's been a long time. It's pre-cal. But remember these. I'll point out on these 2 formulas, they're almost identical, aren't they? The right sides? The only difference is subtraction and addition, right? One way you can remember that, the way that I always remembered it, is subtraction goes with the s here. Subtract, subtract. And then cosine just wasn't that. Okay, that's the way I remembered it. But they both have cosine in them, right? Also, the reason why I like to call this the power reducing formula and not half angle, because that's what it's called in most books, a half angle. Power reducing is because if you look at this as sine squared, right? But in the new expression, you don't have any squared on the trig function. So the power has been reduced, hasn't it? You've actually pulled the power down. But what you gave up for that is that the angle inside doubled. Do you see that? It used to be sine squared of just x. Now in your new formula, you have cosine 2x. So the angle doubled. Yeah? Okay, as long as we're okay with that, we're going to proceed. First example. We're going to do A here. Integral sine cubed for t dt. Yeah. If we see sine by itself, all right, raised to the 3rd power, which is an odd power, isn't it? What are we going to do? So let's look at our cheat sheet that I just handed you. And notice on the cheat sheet, we kind of have it split into 2 columns, like this. Y'all see that? And on the top left, this right here, I want us to read through. It says how to integrate powers of sine and cosine, right? Look at this one. It's 1, 2, 3. Right? For 1, it says if the power of cosine is odd. Well, we don't have cosine, do we? Okay, let's look at 2. If the power of sine is odd. Yes? Okay, so let's see if we can make sense out of what part 2 says. If the power of sine is odd, save one sine factor, and use sine squared x equals 1 minus cosine squared x. To express the remaining factors in terms of cosine x, then substitute u equals cosine x. Yeah, right? Perfect sense. Makes perfect sense. What they mean by save a factor of sine is they just mean peel off one factor of sine. Rewrite this as sine of 4t times sine squared 4t dt. Do you agree that's the same thing? So we have saved one factor of sine here, right? The remaining factor is guaranteed to be an even power of sine, right? Because we started this by saying if that's odd, we're going to peel 1 off, and that means this will have to be either sine squared or sine to the 4th or sine to the 6th or sine to the 8th, right? What we're supposed to do on this is use this. Okay? We're supposed to use the fact that sine squared x can be rewritten like this. Now for us it's sine squared 4t, so I'm going to have sine squared 4t equals 1 minus cosine squared of 4t. So I'm going to rewrite this piece right here using that identity. Sine 4t is 1 minus cosine squared 4t. I need that in parentheses, don't I? It has to be in parentheses because it's 2 terms now, isn't it? It was 1 term, 1 factor, but now using this formula it's now 2, so that sign is multiplying, I have to have this in parentheses. We good? We have the same problem there? And at this point it says, blah, 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 blah. Then at the very end it says, then substitute u as cosine x. So it wants us to make a substitution, a basic substitution now, that u is the cosine part. Let's see what happens. Does anyone see it? If u is just the cosine part of this, not the squared, if u is just this, basic substitution, what's the derivative of that? That's antiderivative. What's the derivative of just cosine? Negative sine 4t times 4, right? Do you see its derivative anywhere? Right there. You see that? This is your basic substitution, the second kind of technique we learned. The second technique that we learned, yes. So I'm going to make my substitution. U is equal to cosine of 4t. Then what do we do once we write this down for basic substitution? Derivative. So derivative of this, du will be negative 4 sine 4t dt. And then we try and match it up, right? We try and come in here and match things together.
Why is it negative?
Derivative, the derivative of cosine is negative sine, not anti. Yeah, so you got to make sure you keep track of all that. Okay, good. Yeah, so you're seeing right now that sine 4t dt is in our integrand, right? So that's this piece right here. So we don't want the negative 4 there, so we scale both sides by negative 1/4. Good. Negative 1/4 du sine 4t dt. I didn't look at your name thing. I'm not going to look at it. Is it Ian?
It is.
Yes. So did you do some work on that this weekend?
I did, actually.
Good. So because you said that, and I know that we had some issues last week on it. So
Yeah, time was an issue, so I needed to finish homework.
well, good. I'm glad that you got kind of up to speed. I can tell. All right. Good. So are we ready to rewrite the integral now?
Yes.
All right. This new integral will become, so you want to take care of this first, this piece and this piece. That's this right here. And I'll bring negative 1/4 out. Negative 1/4, the du, I'll just slap it to the back here. And then the only thing that's left is this piece, which is 1 minus u squared. No, that's just power rule.
Oh, yeah.
That's just because there's 2 terms, you just do them one by one. So what is the antiderivative now? Leave the 1/4, negative 1/4 out here. And I'm going to use parentheses. What's the antiderivative of 1? U. And the antiderivative of u squared is 1/3 u cubed. And that's it? Plus c. What's what?
And you just put in whatever you was.
Oh, that's
Yeah.
the,
You good? No? Okay. Everyone else good? So this is the antiderivative of this. I'm going to replace all my u's now with, I erased it, cosine of 4t. So this is going to be negative 1/4 cosine 4t minus 1/3. How am I going to write this? U cubed. Yeah, cosine cubed 4t. So just place that cubed right there because it's a trig function. That's where we put the powers for trig functions. And then plus c. You could distribute the negative 1/4 through, but that's pretty much you're there. What do you think? That's what you do if you've got sine to an odd power. Pardon, what? There were some of these already, yeah. But that, I think I told someone in here, it may have been you, that they were just kind of get you thinking about this a little bit. All right, so I'd like to do a slight variation of this, okay? It's not part B up there, but let's try this one. What about integrate sine to the 7th of pi x dx. Would this fall into the same category? Yes? Because it's sine to an odd power, so you just peel off one factor of sine. That'd leave you with sine to the 6th pi x dx, something like that, right? But the issue you now run into is how do you rewrite sine to the 6th if we're supposed to use this whole thing with like sine squared x equals 1 minus cosine squared x. If that's sine to the 6th, do we just change this to 6 and that to 6? No. You can do it this way, though. You can say sine squared x cubed, right, is sine to the 6th. Yeah, I'm just using the formula. I'll come back over here and do it here. I'm just saying if we're just manipulating the identity from pre-cal, sine to the 6th would be taking that and cubing it. Agreed? And that means you have to cube this side. And that means you'd have to actually multiply it all out, which I'm not going to. But do you agree that's what it would be? All right. So that's what I'm going to use. I'm just going to say anytime, wherever I see sine to the 6th, I'm going to replace it with this. So come back over here. This is equal to that factor I peeled off. And then this gets replaced with what? 1 minus cosine, bless you, of cosine squared, pi x, all that to the 3rd, right? That's it right there, dx. No questions? Another way, if you're not seeing it this way, okay, you could look at sine to the 6th x as being sine squared times sine squared times sine squared, right? And if each one of these is this, right? This is 1 minus cosine squared x times 1 minus cosine squared x times 1 minus cosine squared x. That's 3 times. That's this, isn't it? Okay. Same thing. So this is where we are. Now we make a substitution. U is equal to cosine pi x. Du will be negative pi sine pi x dx. you're off by a constant. Sine pi x dx right here is what appears there. So I'll have to scale it out. I'll need a negative pi divided that on both sides. So my left side here becomes negative 1 over pi. du is sine pi x dx. Yes?
Since pi is a constant, couldn't it have been scaled out earlier on, or would that have made things tricky?
You mean at what point?
I don't know, probably just before the U substitution, once we'd already done our cosine exchange.
It's trapped, yeah. It's stuck inside the sine function. So you can't pull anything out of the argument of a function, a constant out. All right, so if I do it this way, if I let u be this, and this is sine pi x dx is this, then this integral right here becomes negative 1 over pi, right? That's this integral. Du is at the very end. And then,
Can you just make it u to the sixth, or
no, because it's not u to the sixth. It's 1 minus u squared all to the third. It's 1 minus u squared all to the third power.
but you wouldn't put that in now?
Put what in?
Like you wouldn't cube both of those, or no?
Well, the question now is, what do you want to do with this? Yeah. It's like, so how are we going to handle this? Can you do power rule right now?
No, it's changing first.
So how would you do that then? You want to do another substitution? Not really? What's that? Can't pull a one?
Can you just cube both
Can
of
you
those?
expand it out and integrate each
Yes.
set?
Yes.
Okay.
Because that's cubed, I think that's within the realm of reasonable things to do. Cubing something, cubing a binomial. So what would you get if you took 1 minus u squared times 1 minus u squared times 1 minus u squared, if you did all that? So how about these two together? You get 1 minus 2u squared plus u to the fourth. That's what you would get if you do these two, right? And then out here, 1 minus u squared. And then do it again. So you go here to here, right? The 1 passes through, and then the negative u squared passes through. So you get something like 1 minus 2u squared plus u to the fourth minus u squared plus 2u to the fourth minus u to the sixth. There we go. I think that's it. And some things go away or no? No?
Yes.
No. I think I get 1 minus 3u squareds plus 3u to the fourth minus u to the sixth. That's what you get. Do y'all see that? And that's my new integrand. Isn't it? And then you could integrate each of those, power rule. Is that reasonable to you? I'm going to say here, well, yeah, I'll integrate it. I may as well. No questions, though? So negative 1 over pi. Here comes my antiderivative. Antiderivative of 1, u. Antiderivative of negative 3u squared is negative u cubed. Plus 3/5 u to the fifth minus 1/7 u to the seventh. plus c. And then what's u? Cosine pi x. So you have negative 1 over pi cosine pi x minus cosine cubed pi x plus 3/5 cosine to the 5th pi x minus 1/7 cosine to the 7th pi x plus c. Plus c. And then you could come through and distribute the negative 1 over pi through, if you wanted to. You get the idea here? If we did sine to the 9th power, we could do that. And then what would happen is that this right here would just get bigger. So the expanding part would suck worse each time. But we would have a way of doing it. But didn't we have a reduction formula? We had, do you see the value now of that reduction formula? The reduction formula would save us from having to actually do this. It would, just apply the formula. So, all right. But you're not allowed to have the reduction formula on the test. But I wouldn't give you like sine to the 13th power. I'd give you something like sine to the 3rd, and then ask you to just show me how to do that. Okay, good, good. All right, let's look at the next example, B. What about if we've got sine and cosine together like this? Sine squared x, cosine to the 5th x, dx. Still trying to get that skunk. I got myself another cat today. My second cat in a week. I let him go, though. I let him go. The last one I caught, I kind of relocated. This one, I let him go, like right where I caught him, because he was declawed. So I kind of figured he might be a house cat. And go drop him off in the middle of the woods somewhere with no claws. I don't think he'd do too well. So, all right, so let's look through this. On that part 1, it starts off by saying, if the power of cosine is odd. Hey, we've got an odd power of cosine, don't we? So it's looking like it's part 1. Part 2 said, if sine was odd, sine's not odd. So it's definitely not part 2. What about part 3? If both powers of sine and cosine are even. Well, they're not both even, right? So it looks like we're looking at case 1 here. Okay, so what does it say to do? Save one factor of cosine. So factor out a factor of cosine. And use the Pythagorean identity again. So it's the opposite of what we just did. Instead of pulling a sine out, I'm going to pull a cosine out. So watch. Leave sine squared here. I peel one factor of cosine off, which leaves me cosine to what power? 4th, right? Like that. And then I'm supposed to use the Pythagorean identity, and the one that they suggest I use is this one. So I'm going to turn my cosine squareds into sines, aren't I? So this piece right here, I need to somehow convert it over to sines.
You just separated it.
I could do that. I could do cosine and cosine side by side, or cosine squared and cosine squared. Or I could rewrite that cosine to the 4th as cosine squared squared. Either way, it's going to come out to be the same exact thing. I'm going to do this, which means it'll be 1 minus sine squared x squared, won't it? That's cosine to the 4th. And then that's this squared. So what would this integral look like now? Sine squared x times cosine x times the quantity 1 minus sine squared x, quantity squared dx. Everyone see that? And then at this point, it says to make the substitution, u is sine this time instead of cosine. So let's go ahead and try and make that substitution. I'm going to use red. U is equal to sine x. And the derivative of that is cosine. Yay, it's no negatives or nothing pops out, so that's great. We like that, don't we? And now what we're going to do is rewrite this entire integral. Anywhere where we see a sine, we're going to replace sine x, we're going to replace it with u. Anywhere we see cosine x dx, we replace it with du. So do you see cosine x dx? Cosine x dx right there. That's going to be replaced with du. Right? Everything else has to be accounted for. So this sine squared x is going to be u squared. And this 1 minus sine squared x quantity squared is going to be 1 minus u squared quantity squared. So here we go. U squared, that's this. 1 minus u squared quantity squared. And then the rest is just du, isn't it? And that, again, we could expand out, couldn't we? Like you could actually sit there and take 1 minus u squared, square it, and then pass through. So I'll do that on the next line, I think. I keep on asking if anyone has questions and no one's stopping me. So these seem pretty clear or pretty clean compared to what we've been doing? Yeah? Yeah, it's more of a process, right?
Right.
So when I take this and I square it, I get 1 minus 2u squared plus u to the 4th du. Now distribute the u squared through. So u squared minus 2u to the 4th plus u to the 6th du. And finally, do your power rule and integrate, right? And remember, u was sine x in this one, right?
Yes.
So the antiderivative will be 1/3 u cubed minus 2/5 u to the 5th, 1/7 u to the 7th plus c. And then we replace all of our u's with sine. Oops, 2/5. There we go. So far, okay? So far, huh? We'll do just a few more because I don't want to overload you right before the test. I might even cut you loose early, although I hate to do that.
I'll try to live with that.
You're okay with that?
I'll try to live with you.
Okay. 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 Maybe I shouldn't have said that because it's 12:05 already. But all right, so let's take a look at this one right here. Cosine. Let's just do cosine squared x. Let's start with that. If we have cosine squared x, then does it look like the first, second, or third technique there? Third. Because only one technique has where you have even powers, right? So it says if you got even powers, then use the half angle identities. Well, I'm going to use the cosine squared identity on this one. This is equal to integral 1/2 1 plus cosine 2x dx. That look okay to you? The 1/2 could have come out, couldn't have? I could have pulled that out in the very beginning. But I just want to make sure everyone understood where it was coming from. And then now, just looking at this, I'll put the 2x right there. I won't put it in parentheses, just hoping that everyone understands that's the argument right there. Can you integrate that? Yes, term by term, right? Separately. So going to have 1/2 and then two things. So antiderivative of 1, x. Antiderivative, careful, antiderivative of cosine of 2x. 1/2 sine of 2x. Right? Then
Distribute.
we could. Yes, I just plus c, that's all I remember, plus c. Which would become, yes, if we distribute 1/2 x plus 1/4 sine 2x plus c. That'd be it. That pretty straightforward? That doesn't look so bad, does it?
It gets better.
It's about to get bad. But that seems okay, right? All right, so let's take a look now at part C. So the only difference in part, the one I just did in part C up there is it's a fourth power, right? Instead of x, I'm using beta t dt.
Can you separate it? Well, yeah. I think
Can you,
it's two
how do you mean?
squared,
Yeah, you can make this 2 cosine squareds.
and then just within those.
Yep.
and like the-
Yeah, watch. That's exactly what we're going to do. It's going to be, but instead of doing 2 separate, is it all right if I do this? Like this. Squared. Is that all right if I just write it that way? I mean, we're going to get to the same place. Is that okay? What does this inside piece right here turn into, though? So I'm using the formula, right? It's going to be, and remember, it's all of that squared, right? It's going to be 1/2 times 1 plus cosine, cosine what? 2 beta t. Aren't you supposed to double the angle? And if the angle is beta t, you have to double it, so 2 beta t. So 2 beta t, all of that squared dt. All right, let's make sure we understand this. Cosine squared of beta t is equal to 1/2 times, in parentheses, 1 plus cosine of 2 beta t, close it off, all of that squared. You are not allowed now to go in here and integrate these piece by piece, right? Because it's being squared.
And you can't take the 1/2 out because it's inside the.
Can't take the 1/2 out because it's being squared also. Now you could, because you could square it and then get it out of there, which I will do on the next step. But I just want everyone to understand and appreciate that it's not as easy as the last problem was. Yeah? So here's what I'll do. So what happened there? Just split it up. Because this is multiplication right here, right? If you have two things being multiplied that's being squared, you can square each one of the factors. So that's what I've done. And this 1/2 will come out as a 1/4, won't it? Okay. Let's pull that out. I've got 1/4 integral, and then 1 plus cosine of 2 beta t squared dt. Any ideas? What do you mean?
Same thing.
Expand those out, expand it out. That means square it. You know, square it out. So you have to do this. I'll go slow since it's our first example. You have to go and do 1 plus cosine 2 beta t, right? 2 beta t times 1 plus cosine 2 beta t again. That's what it means to square it, dt. And then you go through and FOIL, right, Ramiro? FOIL. That's funny, Ramiro. I'm going to remember that for a while. You know, speaking of something, y'all don't know what we're talking about. It's an inside joke because he came by my office. Things aren't always the way they appear. I remember growing up, seeing this sign on the side of the road. Like, here's the sign, here's the pole. And it was this sign. I don't know if you've ever seen this before. No, this one right here. Have you ever seen that? It's like the neighborhood watch, right? Have you? Yeah. That's what I thought it was sailboat on a hill. And it's a crook, you know, with his cape and his hat, and that's what it is supposed to be. And it's got like the, you know, no criminals through here. And I remember being like, you know, in grade school and asking my dad, like, why are they saying there can't be ships on a hill in here? And it's like, my dad knew right there. He was in trouble. No, but I'm just saying that, you know, things aren't always the way. You think they're a certain way, and it's like totally not that way. Okay. All right. Do you see what's gonna become a problem as soon as we do this? When we do the last part of this multiplication, we're going to get a what? A cosine squared of 2 beta t. Again, we're going to have cosine squared in here. Let's do it, though. 1/4 integral. We have 1, right? That's our first multiplication. Then when we do the inner ones, we'll get 2 of the cosine 2 beta t's. And then we get plus cosine squared of 2 beta t. So there are the 3 terms we would get if we were to expand that out and collect like terms. Yeah? Can you integrate this? Yes. Can you integrate this?
Yeah.
Yeah. Can you integrate this? Not yet. What am I going to have to do to integrate this? Use the power reducing formula again to bring that power down. Just like the previous example, right? You see that? Right. So I'm going to take care of these two right now. I'm going to take their antiderivatives. And on this one, I'm going to kind of say I'm not able to do it yet. So watch. I have the 1/4 out front. What is the antiderivative of 1? T, right? Because we're integrating with respect to t. So t. All right, now, what is the antiderivative? Careful here. Antiderivative of 2 cosine of 2 beta t. So cover up the 2. What's the antiderivative of cosine 2 beta t?
1/2 sine.
Almost. 1 over 2 beta sine of 2 beta t. Do y'all agree with that?
Yes.
Because the scalar in front of t is 2 beta. So you have to scale by 1 over it. So 1 over 2 beta sine of 2 beta t. 1 over 2 beta times sine 2 beta t. That's what you said? But what's in front of that? A 2. That 2 here cancels. So it's really just 1 over beta sine 2 beta t. Right? Times 1/4. So 1/4 or 1 over 4 beta sine 2 beta t. Jeez. Now, you could have passed the 1/4 through and done it all, you know, however, but we should all get to that. Now, should we check it real quick? The derivative of this is cosine of 2 beta t times 2 beta. And if you multiply that times 2 beta, you'll get 1/2. And so if you multiply 1/4 times 2, you get 1/2. So it does work. So we taking care of the first two? But we still have this one, and we still have a 1/4 out front. So I'm going to put plus 1/4 integral cosine squared of 2 beta t dt. So what should I do on this?
Multiply them again.
This is, we're starting this over. Basically, we're looking at this going, you have a trig function to an even power. Yes? Half angle identity. So I'm going to do the half angle identity on this right here. So this becomes 1/4 t plus 1/4 beta sine 2 beta t plus 1/4 times 1/2 integral 1 plus, you tell me. So this right here, when we use the formula, we get a 1/2, right? The formula has a 1/2 in it. That 1/2 will always be able to come out of the integral. So that came out right here. Do y'all see that? Then it's 1 plus cosine 4 beta t. Because you've got to double the angle again. You see that? The formula says that the power can come down as long as you're willing to double the angle. And if the angle is 2 beta t, it's going to become 4 beta t. So this becomes cosine 4 beta t and then dt. And there's no, we didn't do any integration here, right? This was just a formula to go from here to here. Now can we integrate it? Yes, antiderivative 1, t, antiderivative of this, well,
Beta
1/4 beta
sine.
sine of 4 beta t. Then we'll have to hit it with 1/8. But we'll get to that. So we have 1/4t, 1/4t, sorry, plus 1/4 beta sine 2 beta t plus 1/8 parenthesis, because this 1/8 distributes. Now I'm going to do these antiderivatives. It was just t plus 1/4 beta sine 4 beta t plus c. Do y'all have questions on that part?
Can you just say that again?
That.
The integral part, can you say that again, like, to the answer?
Like,
So you went to, so t here and then,
okay, antiderivative 1 is t, right?
yeah.
Okay, and then antiderivative of cosine of something is sine.
Uh-huh.
But then you have to scale by what's in front of the variable. So 1/4 beta,
Yeah, so beta is just a number.
it's a number. We don't know what it is. And we like to put them in there just to see if you are comfortable with it. It takes a while to get comfortable with it. So it'd be much nicer if that was just 4t,
Yeah.
right? If this were just 4t, you would say 1/4 sine 4t, and it'd be, almost be automatic. With the beta in there, it makes you kind of hesitate. But you get kind of used to it as just being a number that you don't know.
So like beta and pi, they're kind of like the same.
No, beta and pi aren't the same thing. Well,
So if like if beta.
pi is an actual number, like it actually has a value. Beta is a number that I'm not telling you what it is. We'd have to assign a value to it. Pi is actually, everyone agrees what pi is. I'm still not done.
But if you had like 4 pi t,
4 pi t.
like if beta was.
Then this would be 4 pi. This would be 4 pi.
It would still just be 4 pi.
This would be 1/4 pi, yes. But what I was saying is they're not the same in the sense that, hey everyone, what's beta?
You don't know.
We don't, but if I say, hey, what's pi? And everyone would be like, oh, it's like 3.14. Like, we all agree that pi is a certain number. Beta, there's no agreement. Beta is like saying x. Like we don't really know, but we use it a lot for variables. We like to use beta for angles. Alpha, beta, theta, yeah. Still going here. The reason why I'm not done is because there were two terms in here that I could combine together. Yeah, do you see this 1/8 t and this 1/32 beta sine 4 beta t plus c. So just distributing the 1/8 through. This right here and this right here are like terms. So 3/8 t. Agreed? 1/4 plus 1/8 is 3/8. Everything else you could leave alone. These you can't combine together because this one is sine 4 beta t, this one's sine 2 beta t. So, well, I take that back. There probably is some trig identity, some way to get them together, but we're not gonna go for it. This is good enough. But we do want to put the t's together at least. Wow, so that got rather complicated just by raising it up from squared to fourth power, didn't it?
When you grade our tests, like you.
I hate these problems. Yes, I hate these
Yeah, like,
problems.
do you have like a set answer document or anything?
No, I usually make the key every time because I like to time myself and see how long it takes me to take the test.
We were lazy and didn't have the T's together.
That would be one of those, again, those disappointments, you know, where I would be more disappointed in you than anything else.
I'll give you the credit, but
But I couldn't give you full credit. That would be the thing, because if someone did put it all together, then that deserves the full credit, you know? Yeah. Yeah, I put a little, the tier, didn't we talk about the little tiers? With little tiers. Tiers. What's that? Beta. All right, so I think that's probably good to get us at least started with the idea of trig integrals. We still have 20 minutes, but I think this is a good point to wrap it up. What we'll do next time is obviously take the test, but then after that, we'll pick up where we left off, and we're going to start looking at combinations of tangent and secant. When tangent and secant are combined together, and that's the right-hand side of this. And then after that, we get into the trig substitutions. All right, that was trig integrals. All right, everyone, I guess that's it, right? There's nothing else? Test Thursday. I do have office hours tomorrow, 9 to 1, 9 to 12:30. 9 to 12 or 9 to 12:30, yeah, because I usually want to give myself